Unit 2C, applying problem solving steps and using mathematical models. So we're going to use something called Polya's four-step problem solving procedure. So it's broken into four steps on how we actually approach problems and word problems, honestly. So our first thing is we need to do is understand the problem. The best way to start any problem is to write down information that is provided as you come to it. So write down all the big information like numbers. That's what you want to look for, especially with longer word problems. If you read the whole thing all at once and do not do anything, it is easy to get overwhelmed. If you read the problem solving or problem slowly and carefully, writing down information as it is provided, you will always at least have a start on the problem. Another great idea, carefully identify and write down what it is they are asking you to find. This almost always helps you devise a strategy. So it's always good to write down as you go along the information you think is important. And then you always want to write down what are they asking you to do? What are they asking you to find? Step two is to devise a plan to solve the problem. This is where problem solving is at least as much art as science. There are many, many ways to solve problems. Some common strategies, making a list of possible outcomes, drawing a diagram, trial and error, finding similar problem that you can already know how to solve, and using arithmetic, algebra, or geometry. So when we devise a plan with problem solving, it's however you can think of getting to the answer. It doesn't matter how you get to the answer, just get to the answer. It could be by drawing a picture, by just trial and error, by just throwing things together and see what happens. And we're going to practice a lot of different techniques. Step 3, carry out your plan to solve the problem. After you have made a plan, try it out. If it does not work, try a different strategy. There are many different ways to attack problems. Be persistent. So don't give up, just keep trying. Sometimes it's going to take you a few tries to get to that answer. Check your answer. It is always a good idea to think about whether or not your answer is reasonable, and in many cases you will be able to use math to check your answer and see if it is exactly correct. So what you need to do is make sure your answer makes sense. Like if it's wild and outlandish of an answer and it doesn't really fit the problem, you might want to recheck some stuff. Example 1. What necessary piece of information is missing that prevents solving the problem? If a student saves $90 per week, how long will it take to save enough money to buy a computer? So we need to know what's missing in order for us to solve the problem. So if we're trying to save for a computer and we're saving $90 a week, think about it. You need to know something about that computer. You don't need to know about the student's age. That doesn't matter. I don't care how old you are. You're just checking. You don't need to know the date because you're just going to start saving per week. You don't need to know the brand because that has nothing to do with it. You just want something to save towards. And no, not all information is provided because we need to know how much does the computer cost. In order to save $90 per week, I need to know how much do I need to save to. So say my computer's $1,500, I'm going to save $90 per week to get to that. So we're missing the computer price in order for us to solve this problem. A salesperson receives a weekly salary of $300. In addition, $20 is paid for every item sold in excess of 200 items. How much extra is received from the sale of 211 items? What piece of information is not necessary to solve the problem? And how much extra is received? So we need to know what's unnecessary. So we're saying that the weekly salary is $300. So no matter what, $300 a week. And then if you sell over 200 items, you get $20 after you sell that. And we're saying this person sold 211 items. All of this information is very important. We need to know that the threshold is 200 because if you sell over 200, you get $20 per sale. That's what this is saying. You need $20 per sale. Everything you sell over 20 bucks or over 200 items, you get 20 bucks. Because of that, we need to know how many did you actually sell. We need to know that in order to calculate that. And it's super important to know the weekly salary because we need to know how much money are you making. So none of this information provided is unnecessary. You need it all. So all of this information is super necessary. So we need to know how much extra is received. So this person sold 211 items. That's 11 over 200. So this person sold 11 over 200 items sold. So if this person sells 11 items that are extra and you get $20 per item, we multiply. So you get an extra $220. So tickets for a fundraising event were priced at $10 for children and $20 for adults. Shauna worked the first shift at the box office, selling a total of $130 worth of tickets. However, she did not keep a careful count of how many tickets she sold for children and how many for adults. How many tickets of each type, children and adult, did she sell? So we actually have to use trial and error for this because we're not given all the information. So let's proceed by trial and error. We're just saying, suppose Shauna sold one $10 child ticket. In that case, she would have sold $120 worth of adult tickets. Because if she sold only one $10 ticket for a kid out of $130, the rest is adult tickets. Because the adult tickets cost $20 a piece, that means she would have sold $120 worth of adult tickets divided by how much each ticket cost, so that would be 6 adult tickets. We found this answer to the question. Shauna could have collected 130 by selling one child and 6 adult tickets. But that is not the only answer, as we can see by testing other values. So for example, suppose she sold 3 $10 kid tickets for a total of $30, then she would have sold, so if she sold $130 worth of tickets and 3 kid tickets, which are $30, she would have sold $100 worth of adult tickets, which means she sold 5 $20 adult tickets, because 20 times 5 is 100. We have a second possible answer, 3 child and 5 adult tickets, and have no way to know which answers the actual number of tickets sold. In fact, there are 7 possible answers to this question, in addition to the 2 answers we've already found. Other possible answers are 5 child tickets and 4 adult tickets, 7 child tickets, 3 adult tickets, 9 child tickets, 2 adult tickets, 11 child tickets and 1 adult ticket, and 13 child tickets and 0 adult tickets. Without further information, we don't know which combination represents the actual ticket sales. So we can just hypothesize and come up with like, well, she could have done this, she could have done this, she could have done this, but we don't have enough information to actually figure out how much did she actually sell of each. Jill and Jack's race. Jill and Jack ran a 100-meter race. Jill won by 5 meters. That is, Jack had to run only 95 meters when Jill crossed the finish line. They decided to race again, but this time Jill starts 5 meters behind the starting line. Assuming that both runners run at the same pace, as before, who will win? So we're saying that they ran 100 meters and Jill won by 5 meters. So she was 5 meters ahead of Jack, so he only had to run 95 meters before Jill won. But now we're saying, go back, Jill. Let's see if he can win if you start 5 meters behind. So now she has to run 105 meters. We don't know how long it took them, so let's just come up with something. Let's just say it took them 20 seconds. So we're just saying, because it doesn't give us the answer, let's just say it took them 20 seconds to do this race. So we can predict their times by dividing their respective race distances by their speed from the first race, because we know what happened in the first race. Jill won by 5 meters, Jack only had to run 95 meters, and we're saying that it took them 20 seconds to do that. So in the OG race, Jill ran 100 meters because she finished. And she ran that in 20 seconds because we said it was 20 seconds. They did not give us that. We just said it took them 20 seconds hypothetically. So that means Jill did 100 meters in 20 seconds. That's what that means because she ran 100 meters in 20 seconds. So what that means is she ran 5 meters per second. So that little line means per. Fractions mean per, by the way. So she ran 5 meters per second in order to finish the race. Now we need to know how much did Jack run? How fast did he run? So Jack, he only got to 95 meters before Jill won. So Jack ran 95 meters in 20 seconds. So what that means is Jack actually ran 95 meters for every 20 seconds. And that means Jack ran, just use your calculator, 4.75 meters per second. Use decimals, that's totally fine. So now we need to know the new race that they're making Jill start back 5 meters. So for the next race, Jill, remember, she has to run 105 meters. So she does 105 meters and her pace is 5 meters per second. All right, remember, we never actually divide with fractions because that's what we're talking about. We have meters per second. That's a fraction. Remember, we keep change flip. So we keep the first one, 105 meters. Since we're working with fractions, let's make everything a fraction. And then we change the symbol to multiplication, and then we flip the second one. So if we flip it, remember, there's always a 1 underneath, so it'll be 1 second over 5 meters. So we multiply straight across, or you can cross multiply, whatever you want to do. So 105 times 1 second is 105 minutes per second. And then 1 times 5 meters, that's 5 meters. Because meters are on top and bottom, we cancel those out. So we have 105 seconds divided by 5, which is 21 seconds to finish. So with her pace from the first race of 5 meters per second, if she needed to race 105 meters now, she's finishing this race in 21 seconds. Now we need to know Jack's time. Jack is still only running 100 meters. He hasn't changed positions, so Jack is still only running 100 meters. And Jack runs that time in 4.75 meters per second. Because we have meters per second, that is technically a fraction, so we keep change flip. Remember, there's always a 1 under everything. So we keep the first one exactly the way it looks. That's 100 meters over 1. We change the sign in the middle to multiplication, and we flip the last one. So it'll be 1 second over 4.75 meters. You can multiply straight across, or you can cross multiply. It's up to you. You're going to actually have to multiply straight across. You can't cross multiply here. So 100 times 100 meters times a second, that's 100 meters per second. Then we have 1 times 4.7 meters, so that's just 4.75 meters. Because meters and meters are both on top, we cancel those out. And when we put that into our handy dandy calculator, 100 seconds divided by 4.75, we get 21.05 seconds to finish. So it takes Jack still longer to finish. So what this means is Jill is still faster by 0.05 seconds and will still win the race. Example 5. The cars in the Canary. Two cars 120 miles apart being driven towards each other on a long straight highway. One car travels at 20 miles per hour and the other at 40 miles per hour. At the same time, a canary starting on one car flies back and forth between the two cars as they approach each other. If the canary always flies at 150 miles per hour and turns around instantly at each car, how far has it flown when the cars meet? Okay, so straight up it says 120 miles apart. That's a really big deal. Anything with numbers you usually want to pull out. So 120 miles apart. All right, then we're talking about two cars. So one car is traveling 20 miles per hour, the other car is driving 60 miles per hour, or sorry, 40 miles per hour. So the cars will approach each other at 60 miles per hour. Why? Because one is traveling at 20 and one is traveling at 40. So when they come together, it's 60 miles per hour. So if they're 120 miles apart and they're driving 60 miles an hour, we can actually find how long it takes them to reach each other. So they're 120 miles apart, and we're going to divide by how fast they're going, which is 60 miles per hour. Now, we are working with a fraction here because miles slash hour, that's miles per hour, that's a fraction. So we keep the first one exactly the way it looks. So that's 120 miles over 1. Remember, there's a 1 under everything. So we just keep it as a placeholder. We change the symbol in the middle to multiplication. And we flip the second one. So that'll be 1 hour over 60 miles. We multiply straight across or cross multiply. It's totally up to you. So we have 120 miles per hour over 60 miles. Because we have miles on top and bottom, we cancel those out. We're left with hours. So 120 hours divided by 60 is 2 hours. We always want to be left with one unit of measurement here because it's asking about time. So 2 hours. So what this means is that the cars will meet in 2 hours. Now we're talking about the Canary. The Canary is flying at 150 miles per hour, super fast. So they said that the Canary is flying back and forth from the two cars. So it goes to one car to the next. So it's traveling 150 miles an hour for 2 hours. Because that's when the cars will meet. We're asking how fast is it flown when the cars meet? The cars meet in 2 hours. So we just multiply by 2. 150 miles per hour times 2, we get 300 miles. So if you're traveling 150 miles per hour for 2 hours, you have traveled 300 miles. So, Zeno's paradox. This dude Zeno came up with a bunch of awesome mathematical paradoxes, which is he's really fascinating. You should look him up. The Greek philosopher Zeno, 460 BCE, posed several paradoxes that defied solution for thousands of years. A paradox is a situation or a statement that seems to violate common sense or to contradict itself. One paradox begins with the imaginary race between the warrior Achilles and a slow-moving tortoise. The tortoise is given a head start, but our common sense says that the swift Achilles will soon overtake the tortoise and win. Zeno suggested a different way to look at the race. Suppose that, as shown in the figure, Achilles starts from point P0 and the tortoise starts from P1. During the time it takes Achilles to reach P1, the slow-moving tortoise will be ahead a little bit to P2. While Achilles continuing on the P2, the tortoise will move ahead to P3, and so on. That is, Achilles must cover an infinite set of ever smaller distances to catch the tortoise, that is, from P0 to P1, P1 to P2, so on. From this point of view, it seems that Achilles will never catch the tortoise. The paradox puzzled philosophers and mathematicians for more than 2,000 years. Its resolution depends on a key insight that became clear only with the invention of calculus in the 17th century. It does not necessarily require an infinite amount of time to cover an infinite set of distances. For example, imagine that the infinite set of distances covered by Achilles begins with 1 mile, followed by half a mile, followed by quarter, and so on. Then the total distance he covers in the miles is. So we're saying that every time you meet the next threshold, so it goes from 1 mile to a half, to a quarter, to an eighth, to a 16th, to 132, 164th, all the way forever. You can keep halving it forever. This sum is called an infinite series because it is the sum of infinite numbers of terms. You might guess that an infinite series would sum to infinity, but note what happens when we add just the first 4 terms, then the first 8, and then the first 12 terms. You can confirm the following result with the calculator. You can add them all up if you want to. If you continue to add more terms in this infinite series, you will find that the sum gets closer and closer to 2. It will just keep getting closer and closer to 2 because the person, Achilles, is going from P0 to P1 and then P1 to P2. So in order to keep approaching, you can infinitely just make smaller and smaller increments to get to P2. Therefore, even though the paradox has Achilles covering an infinite number of even shorter distances, the total distance he runs is finite. In this example, it is 2 miles. Clearly, it won't take him long to run finite distance of 2 miles, so he'll pass the slower tortoise and win the race. So that's what it's saying here. That starting point of Achilles is 0, starting point of the tortoise is 0, or is P1. Achilles runs from 0 to 1, the tortoise runs from 1 to 2. Achilles runs from P1 to P2 infinitely, but the tortoise is already moving to P3. That's just a paradox, right? It's like, wow, that's like a mind trip. It makes sense, but it doesn't make sense. It's just a little bit of history about mathematical paradoxes for you. All right, suppose you have 2 cups in front of you. One holds coffee and one holds milk. You take 1 teaspoon of milk from the milk cup and stir it into the coffee cup. Next, you take a teaspoon of the mixture in the coffee cup and put it back in the milk cup. After the 2 transfers, there will be either 1 more coffee in the milk cup than the milk in the coffee, or 2 less coffee in the milk cup than the milk cup in the coffee. Or 3 equal amounts of coffee in the milk cup and milk in the coffee cup. Which of the three possibilities is correct? So this is what we're doing. We have 2 cups, coffee and milk. We take a teaspoon of milk, put it in the coffee, and then we take a teaspoon of the coffee and put it back in the milk. A cup of milk or coffee contains something like a trillion molecules of liquid. Clearly, it would be difficult to visualize how such enormous numbers of molecules mix together, let alone calculate the result. However, the essence of this problem is the mixing of the 2 things. So one approach is to try similar mixing problems that is much easier, mixing 2 piles of marbles. So because we can't think of trillions and trillions of molecules, what we do is we break it down into small things like marbles. Use easy sets like sets of 10. So we have the milk. So let's say the milk has 10 marbles in it, 10 molecules. So that's our 10 molecules of milk. And then we have coffee. So we're also saying that the coffee has 10 marbles of milk. So what we're saying is we're putting milk into the coffee. So let's put 2. So we're getting rid of 2 from the milk pile. So when we draw it, get rid of 2. So we got rid of 2. Now we only have 8 left, and we're moving them to the coffee. So now the coffee has 12. So moving 2 milk marbles to the coffee is the teaspoon. That's what we're representing to be the teaspoon. Representing the second transfer, of 1 teaspoon from the coffee cup into the milk cup involves taking any 2 marbles from the black pile and putting them in the white pile. We can then ask the question to the original question. Are there more black marbles in the white pile or white marbles in the black pile? Because the marbles represent molecules that mix together, the 2 marbles for the second transfer must be drawn at random, which represents 3 possible cases. The 2 marbles in the second transfer can be either both black, both white, or one of each, because it's random, we don't know. So we can take random marbles. We can take 2 of the black, 2 of the white, or one of each. So that's what we're doing here. We can transfer 2 marbles back to the white pile. The 2 marbles may be both black, they might be both white, or one of each. In all 3 cases, we end up with the same number of white marbles in the black pile as the black marbles in the white pile. So this is if we, so this is, so all of this is random. So 2 black marbles transferred, we're still left with 2 white here, and then 2 goes back to the white. One of each, so if we do 2 white marbles in, so the white goes away from here and it goes back to the original. One of each, so we have 1 in the white milk, we have 1 in the coffee. The only remaining step is to confirm that the simpler problem is a reasonable representation of the real problem. Our choice of using 2 marbles to represent a teaspoon was arbitrary. If we redo this example with transfer 1, 3, or any other number of marbles, we will find the same result. We will always end up with the same number of black marbles in the white pile as white marbles in the black pile. Starting with 10 marbles in each pile also was arbitrary, meaning it doesn't matter. The conclusion remains the same if we start with 20, 50, or trillion marbles. Because molecules can be thought of as tiny marbles for the purpose of this problem, the real problem has no essential difference from the marble problem. So imagine this is a great way to break down what we just did. Imagine you have two cups, one with just coffee and one with just milk. Now we're going to play a little game. First, you take a little milk and mix it into the coffee cup. Now the coffee cup has a mix of both coffee and milk. The milk cup still has mostly milk, but it's missing a little bit you took. So you took some milk, you put it in the coffee. Now the coffee has a little bit of milk, and the milk is still just milk in that cup, but it's missing a little bit. Next, you take a little spoonful from the mixed coffee cup and put it back into the milk. Since the coffee cup has both coffee and milk now, the spoonful you take will also have that. It will also have coffee and milk. That means you're putting back some milk and some coffee into the milk cup. Now here's the magic part. The amount of coffee that ends up in the milk must be the same as the amount of milk that stayed in the coffee cup. Why? Because you move the same amount of liquid both times and everything mixed evenly. So after all that swapping, there's just as much coffee in the milk cup as there is milk in the coffee cup. It's fair and even, just like sharing a snack with a friend. Alright, let's actually do some solving. So party decorations. Juan is decorating a party in a room that has 10 large cylinder posts. The posts are 8 feet high and have a circumference of 6 feet. His plan is to wrap 8 turns of ribbon around each post from bottom to top as shown. I took away the figure, my bad. We're going to draw the figure. How much ribbon does Juan need? So you're setting up for a party and you want to wrap ribbon around the post. You want to make sure you have enough ribbon because I don't know if this ever happened to you where you run out and you're like, oh my gosh, I have to go back to Party City and grab more. So we need to know how much ribbon do we actually need. So we're going to draw the picture. We're talking about a cylinder post, a cylindrical post. So think of like a Coke can. So a cylindrical post is like a soup can or a Coke can. It's like this. So that's a cylinder in 3D. I'm so bad at drawing 3D. So it's saying that this cylinder is 8 feet high. So this is 8 feet. And the circumference is 6 feet. So remember, circumference is all the way across. So it's like kind of like the thickness of the pole. And you have 8 of them. So how do we even approach this? Because we really don't know much about cylinders. However, if you unfold a cylinder, it's actually a rectangle. You ever take a wrapper off of a soup can or you take the wrapper off of like a Coke bottle? Doesn't it come out to be a rectangle? when you unwrap the little piece of paper there. So if you unfold a cylinder, it actually is a rectangle. So this rectangle that we're talking about, it'll look like this. So it's 8 feet high, because that's how tall the cylinder is. And it's 6 feet wide, because that's how wide the cylinder is. So we need to wrap this 8 times. It says it right here. Plans to wrap it 8 times or turns around it. So what that means is it needs to be separated by some type of distance. So if it's 8 feet high and you need to wrap it 8 times, that's 1 feet per time. So it's actually 1 feet per turn, but we're going to say 1 feet separation, because each ribbon will now be separated by 1 foot. So if we wrap it 8 times, let's go ahead and draw that. I will do my best. I am so bad at drawing stuff like this. So we're wrapping it once, twice, 3, 4, 5, 6, 7, 8 times. That is the best way I can draw that. I'm so bad at it. But we just found out that it's actually separated, it's spaced out by 1 foot. So from here to here, and all those spaces is 1 foot. Do you notice that we have a triangle? I'm going to really make it known to us. We have a triangle now. So each piece wrapped around is actually a triangle. I'm going to bring it out. So we know that this part right here is 1 foot. All the way across is 6 feet. So from here to here is 6 feet. Actually, I drew that upside down. Let me redraw that so it doesn't confuse us. So I drew that upside down. Let me redraw it. There we go. So from here to here is 1 foot. And all the way across is 6 feet, because that's how wide the pool is. Or the pole is, the pool. So we need to find the missing side. In order to find the missing side, you use the Pythagorean theorem. Now, coming into this class, you are expected to know certain things. To find the missing side of a right triangle, we use the Pythagorean theorem. The Pythagorean theorem is leg squared plus leg squared equals hypotenuse squared. So that's what we're trying to find, is actually the hypotenuse. The hypotenuse is the diagonal one. So our leg, they're interchangeable. Whatever leg you want to put first, you could put first. It doesn't matter. So the first number I see is 1. So I'm going to do 1 squared. Then we're going to add that to our second leg, which is 6. So 6 squared. And the hypotenuse, which is the diagonal one, it's not the straight one. It's the one that cuts across. That's what we're trying to find. So we don't know it. We say x. You can use any variable you want, but we say x in math. So let's simplify. We have now 1 squared is 1. 6 squared is 36 equals x squared. 1 plus 36 is 37 equals x squared. And then to get rid of a square, you square root it. So you square root to get x by itself. So we get about 6.1 feet equals x. So that means this part right here is now 6.1 feet. So that's the length of the ribbon, because that's how much we're wrapping around. So the length of the ribbon segment is 6.1 feet, and we need 8 of them because we're wrapping it 8 times. So 8 times 6.1, and we get 48.8 feet. So that's how much we need per post. But we have 10 posts. It told us that we have 10 posts that we need to do. So we need to figure out how many for all. We have 10. So we need to multiply that by 10. So 10, which is how many we have, and we need 48.8 feet for each, and that comes out to 488 feet of ribbon. China's population policy. In an effort to reduce population growth from 1978 through 2015, China had a policy that allowed only one child per family. The policy succeeded in dramatically slowing China's population growth, but it also had a number of unintended consequences. One particular troubling consequence was that, because of cultural bias towards sons, many Chinese found a way, primarily through selective abortions, to make sure that their child was a boy, which caused China's population to end up with far more young men than young women. To address this unintended consequence, one popular proposal suggested replacing the one child policy with one son policy, in which families would be allowed to continue having children until they had a son. That is, if a family's first child was a boy, the family would have met its limit of children, but if the first child was a girl, the family could have an additional child until one was a boy. So suppose that one son policy has been implemented at birth rates returned to their natural levels, about half boys, half girls. Compared to the one child policy, how would the one son policy change the population and proportions of boys and girls? Assume that most families would choose to have a son under the one son policy. And B, China did not adopt a one son policy Instead, as of 2016, China suggests changed its one-child policy to a two-child policy. How does the population impact of two-child policy compared to that of one-son policy? Assume that most families would choose to have both children allowed under the two-child policy. So, to answer A, most people initially approach this problem by noting that under one son policy, half the families would have a boy and their first and only child. Of the remaining, half would have a boy as their second child, reaching their one son limit, while the other half would have a girl and go on to the third child. Half of these families would have a boy on the third try, while the other half would continue on after a third girl, and so on. However, a moment of insight makes the problem much easier. Since we are assuming that one son policy would restore natural birth rates, roughly equal number of boys and girls would be born. And if we assume that most families would eventually have exactly one boy under this policy, then having equal number of boys and girls overall would lead to an average of one girl per family, and hence an average of two children per family, one boy and one girl. Therefore, the one son policy would double the average number of children per family from 1 to 2, while restoring the population of children to being about half boys and half girls. If most families choose to have both children allowed under the two children policy, this policy obviously would produce double the total number of children produced by a one child policy. So, in terms of population growth, the impact of two child policy and one son policy would be the same. The main difference is that under the two child policy, many families would end up with both children being girls. Probability tells us to expect 1/4 of the families to have two girls, because if we use B for boy and G for girl, GG is just one of the four possible birth orders. So if you're having two kids, you can either have girl girl, girl boy, boy girl, or boy boy. No other order. Therefore, a cultural bias towards son might lead families to look for ways to have a son, in which China might still end up with more boys than girls being born.